I am now sharing my screen.
Good evening, madam.
The slide is visible to all of you.
Good evening, ma'am.
The slides are visible.
Yes, ma'am, visible.
Yes,
Okay,
ma'am.
okay. My sound actually just it was minimized. Okay, no problem. So we will start today's class. Actually, reactive intermediates part 2, in which we have free radicals, carbenes, nitrines, and arine intermediates. So first of all, we will start with your free radicals as intermediates. So how these free radicals are generated? This is by the homolytic bond cleavage. Homolytic, which yesterday I also discussed about homolytic and heterolytic. So by homolytic bond cleavage, that means one of this take one electron. So here, whenever you will see that this kind of radical reactions, you do not put a arrow like this, as it represents the transfer of one electron. So we represent a fish hook arrow like this. So each of the atoms which are bonded actually, so that would take one electron, so that is known as your homolytic bond cleavage. So we do it by many methods. One is your photolysis, like in presence of light. So if you just see this ketone in presence of light, it first cleaved homolytically to give you your acyl radical as well as your methyl radical. Again, this uh, acyl radical undergoes cleavage to give bond cleavage to give you carbon monoxide and methyl radical. Similarly, your this diazo compound also in presence of light, that gives your R dot, that is your alkyl radical with nitrogen gas. Okay, even chlorine molecule, when in presence of light or in if you heat it, that undergoes homolytic bond cleavage to give you two chlorine free radicals. Even by thermolysis, like I told you, when we give heat, so that also gives a free radical. So this benzoyl peroxide, it is mostly used in the actually chain polymerization reactions. So in that case, your benzoyl peroxide first cleave on this bond to give benzoyl oxyradical. Again, this benzoyl oxyradical actually benzoyl oxyradical again bond cleavage occurs to give you two phenyl radical and carbon dioxide molecule. So this AIBN, that is also another initiator, 2,2-azobis isobutyronitrile. When that also cleaved, this bond is breaking to give you two radicals, which is actually, you can just see this one is also resonance stabilized and nitrogen gas is released. Similarly, you can do generate your free radicals by redox reactions. Redox reactions means oxidation transfer reactions. One would be your reducing agent, one will be your oxidizing agent. So as you can just see here, we have taken a ferrous ion. Ferrous ion is converted to ferric, that means it has been oxidized, so other part must be reduced. So this hydrogen peroxide in presence of ferrous ion, it converts to OH minus and OH radical. Okay, similarly, your acid anhydride in presence of cuprous ion, that gives you cu- cupric and one uh, acetate radical and acetate ion. So this acetate, even through electrolysis also you get your radicals, like uh, when this acetate ion at anode, it releases one electron to get you acetate radical, which often removal of actually carbon dioxide, that is a very good leaving group. Carbon dioxide is released to give you R dot. We may undergo dimerization to give you RR. So there are different methods for the generation of your free radicals. Next comes the structure and stability of free radicals. So as we know that your free radical means it has an unpaired electron, so it can have either sp2 hybridization or sp3 hybridization. In case of sp2 hybridization, it is planar structure, and the and the unpaired electron remains in your p orbital. But in case of your when it is of sp3 hybridization, the unpaired electron will remain in your sp3 hybrid orbital. It depends on actually the R groups. Actually, as you can just see, when we remove hydrogen with fluorine, the s character of your carbon increases. That means this one can be sp2, but again s character okay, the s character of the half-filled hybrid okay, increases across the series as depicted below. So if this is sp3, then sp character, it increases, it can be sp2. So depending on the substituents, it can be of planar structure or pyramidal structure. Okay, this pyramidal structure actually, it is a three-dimensional structure, so this can be chiral, but actually it gets flipped immediately, so that you always get a racemic product. So as for example, if you just see this chiral alkyl halide, when it is treated with chlorine dot, so it undergoes first your initiation, chlorine will take out this hydrogen, so minus HCl, and you get a free radical. So one electron in your p orbital, so it is the possibility that it can attack from both the sides, resulting in the racemization of the product. Suppose you start with R, you are getting R plus S. So if you say that, okay, if you have pyramidal, then you could have a actually enantiomerically rich compound. But this pyramidal shape, actually this undergoes fast racemization, and it can give you a planar free radical, which results in your racemization of the product. Next is the okay, this how they are getting stabilized. If you just see, this can get stabilized when there is a presence of a pi bond just adjacent to it, so that it can get delocalized by your resonance. Similarly, this benzyl radical also gets stabilized in this way. But if you just see, it can have planar structure as well as your planar structure as well as your pyramidal structure. So in case of this bridgehead positions, you just see this is possible for a radical to be there, but it is difficult for a carbocation to be present at this position, because this bridgehead position cannot be planar actually. So this one is not observed, but in case of your free radical in a bridgehead position, it is possible, because it can acquire a pyramidal geometry. It does not have to be planar. It can go from your planar to pyramidal. So, but carbocations or carbanions cannot have this type of geometry. Okay. Next is stability of free radicals. We know there are many effects, inductive effect. So tertiary would be more stable as compared to secondary, as compared to primary, which would be more as compared to your methyl. Even hyperconjugation also, you can just see, whenever you have a hydrogen just at the adjacent carbon, it can undergo actually hyperconjugation. So the more the number of CH3 groups attached to this carbon, the more the stability would be of the free radical. Even resonance also, it can delocalize onto your pi system when it is in conjugation with a carbon-carbon double bond. So as case of in your allylic radical, and this is the case of your benzylic radical. So you would have more resonating structures possible in case of your benzylic radical, and so that would be more stable as compared to your allylic. Again, while comparing this with your normal tertiary, secondary, primary, and methyl, then actually resonance is a stronger effect as compared to inductive effect. So in that case, your benzylic would be the most stable radical as compared to allylic. Then comes your tertiary, secondary, primary, and methyl. Okay, if you have two more phenyl rings attached to it, like in our benzyl radical you were having three four resonating structures. When you have another two phenyl rings, then your conjugating structures or resonating structures or contributing structures increases. So that means its stability increases. So you just see in case of benzyl radical, that is more stable as compared to allyl, as compared to tertiary, as compared to secondary, primary, methyl, then comes your vinyl, alkyl, and phenyl. So it is of the same order in case of your carbocation intermediate stability. Again, stability formation, actually this radical is stable in presence of steric groups. As you can see, this radical can be actually uh, can be you can just say it can be identified because of this steric hindrance, no other radical will approach this O dot or this radical to form a dimer or to form any kind of compounds. So in presence of steric groups, this radical is once it is formed, it is stable. Uh, Okay, how that free radicals are forming, how you detect them. Addition of a radical inhibitor or radical initiator. Actually, if you just add another chemical which inhibits the growth of your radical by just suppose we have R dot in our reaction mixture, it is reacting, we just purposefully add another radical initiator, suppose any X dot. So what it would do, that it would just quench the reaction, like it would just eat all the free radicals which is present in our reaction, so reaction will stop. So that is one kind of detection of free radicals. By trapping the reaction, you can just trap it with another kind of a compound. Again, this one is the most actually effective technique, that is known as your electron spin resonance spectroscopy. So this spectroscopy detects your free electrons or unpaired electrons. What it does, actually it has like our electrons are behaving like your spin magnets. So whenever one magnetic field is applied there, then it will have two states. One will be aligned with the magnetic field and one will be aligned against the magnetic field. So which one is aligned with the magnetic field, that would be of lower energy, and which one is aligned against the magnetic field, that would be of higher energy. So these states, these are your spin states of your electron. So in the ground state, in the presence of your magnetic field, the electron will remain in your ground state. When your electrode, this in ESR spectroscopy, they use your microwave radiation. So when microwave radiation is given to that, then this electron will go to the higher energy. So that gives you a spectra. So depending on which kind of electron or which kind of environment it is present, in which kind of environment it is present, that energy difference will vary. So that is the principle of your ESR, electron spin resonance spectroscopy. So if you have a free radical, you would get a peak. And also this gives an indication of in which kind of environment it is present. As you need see that this one is of yours methyl radical. So actually if it is in the close vicinity of number of protons, then that would give you the peak. So if it is in the close vicinity of n number of protons, then that would give you a n plus 1 peak. So here you have 3 protons, so that is giving you 4 peaks. So ESR gives a clear indication of whether you have a free radical, and if you have a free radical, which kind of free radicals you are having. So in the case of 1, 2, 3 cycloheptade trying, you can just see it has 1, 2, 3, 4, 5, 6, 7, 8. 8 actually 8 peaks are there. That means it is having 7 protons in its close vicinity. Ah, the slide is not moving. Am I audible?
Yes, ma'am.
Yes, ma'am.
But the slide is not moving. I think my tab got hanged. I will be back in 2 minutes. Okay. I will just
Okay.
Okay,
restart my
ma'am. Okay.
system. Yeah, I will just restart my system and I will be back in 2 minutes. Okay, I am back. Now I'm sharing my screen. Okay, now the screen is visible.
Yes, ma'am.
Yeah, and it is sliding. Okay. Uh, Sometimes some this system. Okay, so we have discussed about our electron spin resonance spectroscopy. Uh, then, what is the mechanism of free radical reactions? Wherever you will see free radical reaction, most of the time you will say that it goes through three steps. First one is your initiation, propagation, and termination. Even polymerization also, we just go through these three steps: initiation, propagation, and termination. So I forgot to write here as termination. So for the initiation, that means we should generate a initiator, or sometimes you just use uh, as you see, you have just put in presence of your light, chlorine gets actually the bond between chlorine bond cleaved to give you chlorine free radicals, or you heat it, you generate say free radical, and then the propagation goes. Uh, uh, so first in your initiation you get one free radical, then in the propagation step that attacks to your substrate, which is your actually organic compound or whichever substrate you are having. Then in each of your propagation step, you will see that there is a generation of another free radical again. So the chain goes on. So this one will attack here, that gives you a product CH3Cl. Again Cl radical is formed, so again this Cl radical will attack another molecule of your methane, and that generates your CH3 dot. Then this goes on, that is your propagation. So here this radical like chlorine dot which helps to propagate is also known as your chain carrier. Okay, as termination, when termination happens with the progress of reaction, the number of your radicals, uh, actually the concentration of radical becomes more and more. So when two radicals meet each other, then it forms a neutral compound, it forms a compound. So that is your termination process. So all the free radical reaction, most of the free radical reactions passes through initiation, propagation, and termination steps. First one is your SRN1 mechanism of free radical reaction, that is substitution radical nucleophilic unimolecular reaction, because the rate of reaction depends only on the concentration of one of your substrate. Okay, this involves your radical anions. So first what happens, it generates a radical anion, ARX takes one electron to give you ARX dot minus. Then it goes on propagation. First it would give you a radical AR dot plus X minus, then AR dot reacts with another of your nucleophile. Okay, so nucleophile ARY dot minus. So again ARY dot minus will react with another of your substrate to give you product ARY and ARX dot minus. And overall you can just say ARX plus Y minus, means that is a kind of nucleophilic substitution reaction only. Okay, nucleophilic substitution reaction only. uh, but it passes, goes through this free radical mechanism. Just here you just see it is our starting material, that is from okay, it is here. From this you just take one electron, so that gives you anion radical. So this anion radical loses, this bond is actually broken. You have already one electron here, so you would get a radical here. Okay, so this radical will react with your nucleophile to give you nucleophile radical anion. So this nucleophile radical anion reacts with another molecule of your ARX to again regenerate this radical. So this process goes on. So there is one case effect where you do not have a non-chain SRN1 reaction. What happens here? It occurs in your solvent cages. So in solvent cages, if it occurs, so there is a chance of actually only maybe one molecule or two molecules. So it does not have a chance to react with the initial substrate. Suppose you just see this one. In this case, actually first what happens, the it forms the radical anion. So again, this radical anion, your I minus is removed, and you get your this radical. So it immediately reacts with this one because that is already in your solvent cage. It does not react with another molecule of this one. It does not have the chance to react with this one. So it only gives you the product. It does not undergo a chain reaction. Each step you are getting the product, only product, then again they are reacting and you are getting the product. In that case the chain reaction does not occur. So this is an example of non-chain SRN1 reaction, because it is mostly happens in case of your dilute solutions when you have many solvent molecules. So we have different type of free radical reactions. Substitution reactions, when one group is substituted. So first substitution reaction is your halogenation, where we will have chlorination, bromination, iodination, and fluorination. So for chlorination, if you see, chlorination is highly exothermic. Exothermic. So here you get a number of products. Selectivity for a special product is very less. If you just see, the first step is event endothermic, but these two steps are highly exothermic. So selectivity is less in case of your chlorination, but in case of bromination, as you see, the first step is quite endothermic, and second step is exothermic. So this one is not highly exothermic, so the reaction is controllable. So you can just control the reaction in case of your bromination. What about your iodination? Okay, bromination, sorry, we have another bromination. So when you need a controlled bromination or allylic bromination, in that case there is another reagent, that is your N-bromosuccinamide. This is your N-bromosuccinamide. So what it does not give you a large amount of bromine, so it gives you very less amount of bromine. So in the reaction condition or in situ, it will generate bromine. Once bromine is reacted, then again bromine will be formed. So in this reaction, actually the bromination takes place at the allylic position. So this is mostly your allyl bromination. Uh, okay. But I was saying that in chlorination is exothermic, so that was not very selective. Bromination is selective, like you can get your selected product. In case of iodination, this one is very slow. As you can see, it is highly endothermic. It requires more energy. And this step is of less, means it releases energy, but these two steps are endothermic. So this is quite actually slow reaction. Again, iodination, as you know, that iodination is a reversible reaction, because HI which is being formed, that again that is a highly reducing agent. It itself gets oxidized to iodine. So iodination is actually reversible. So direct iodination mostly we do not do. Next comes your fluorination. As you can see from these last two steps, these are highly exothermic. So this reaction is not controllable in your laboratory manner. Whenever they do, even in the dark also, even at 190 Kelvin or 95 Kelvin, so negative temperature, in the absence of chain inhibitor also, you can, then only you can do the reaction. So fluorination is highly active, so highly exothermic, so very reactive. Chlorination is a bit less reactive, but still it is not very selective. Like in chlorination, if you just wanted this product, will not end at this product. You are going to get a CH2Cl2 or CHCl3. So it will give you a large number of products, so that is not selective. But in case of bromination, you will get your product, actually the required product, selectively. So and iodination is very slow. Next is what is the polar effects in halogenation. So whenever we have a polar group in your mm, substrate molecule, suppose in this case we have a polar group, that is chlorine. So if you just see, we have actually three secondary hydrogens and one primary hydrogens, but still you just see the rate of reactivity is more in case of your CS here. Actually if you just see, if we have a radical, we are generating a radical here, that should make it more stable because of the presence of an electron, uh, electron donating, means this, chlorine is an electron withdrawing group, also chlorine is also an electron donating group through resonance. So actually if you just see, this should be more reactive, but this doesn't happen. This gamma hydrogen is more reactive, means chlorine has to attack on this position as compared to this position or this position. Even this one is, this primary hydrogen removal is more as compared to your secondary of this two. Actually what happens here, already we are having a polar group present here, so the attack of another polar group is being repelled by this polar group already present there. So similar is the case with your actually chlorination or bromination of this, our propanoic acid, which is more in case of your beta hydrogen. Beta chlorination would be more as compared to your alpha chlorination. Okay, next comes your addition reactions. In case of your addition reactions, uh, in case of addition reaction, this is, we get, suppose we have bromine dot, so so your trans bromine, okay, that goes and to give this one, again bromine would be removed to give you this product. Okay, so this one is, addition of chlorine or bromine to ethene is highly exothermic, so this takes place readily, but addition of iodine is endothermic, so that is difficult to achieve. So which is, this is a reversible reaction, so you can just easily see that this is a very good reaction to do the cis trans, actually isomerization. So this is a bromine catalyzed isomerization of your cis dichloroethane. You just see this one is your cis. Okay, so now this cis, cis dichloro ethene is attacked by your bromine to give you this radical, which again can be, this radical will be again removed to either give you cis or trans. So this is a good method for the cis trans, for isomerization of your butanes. So mostly cis will be transferred to your trans isomer because that is more stable, so that predominates in your reaction mixture. Okay. Next comes your addition of halogen acids. This is actually when we have done with HBr, only HBr in presence of nothing, just we add alkene with HBr. There we get a 2-bromopropane. So that is your Markovnikov's rule. Because in case of your addition, in this case your proton is added first to give you a more stable carbocation, which is your secondary carbocation, then bromide attacks to give your 2-bromopropane. So Markovnikov's rule says that the addition of any unsymmetrical alkene, addition of an addendum to an unsymmetrical alkene happens in such a way that the negative part of the addendum goes to the carbon containing more number of substituents. So negative part is here bromine, so that goes to the carbon having more number of substituent, so this carbon. But in case of your, whenever you are using HBr in actually peroxide, that is also known as your Kars effect, or in presence of light, so that generates a bromine radical. So this, in this case actually bromine radical attacks here first, generating a free radical. So it can either, bromine can either go to this carbon to generate a secondary free radical, or bromine can attack carbon number 2 to generate a primary free radical. We already know that secondary free radical is more stable. So next step is nothing, just your abstraction of proton radical from your HBr to give you 1-bromopropane. So in this, this is also known as, this is anti-Markovnikov's rule product, anti-Markovnikov's product, and this effect is known as your Kars effect or peroxide effect. Okay, so in radical only in case of HBr you have radical addition, but in case of HCl and HI you do not see any Kars effect, so that doesn't happen actually in case of your addition of HCl and HI. Next is your auto oxidation. Whenever your free radicals are present, or when your free radicals are actually in free radicals are present in air, or you are just put in exposure to air, that generates actually this kind of uh, dioxygen free radical. Okay, and that again abstracts one hydrogen from your any alkyl group to form your hydroperoxide. So you just see in this reaction, you have a hydrogen here. So first it generates a radical, then it reacts with oxygen to generate this hydroperoxide. So sometimes you see many chemicals when exposed to sunlight and air, that gets oxidized, auto oxidized. There we are not giving any oxidizing agent, just in presence of air it gives you an hydroperoxide. Okay, so you just see this reaction. In presence of light, this gives you this di radical, which again reacts with oxygen. We know that oxygen would be like this. So you would get a bond here, and another radicals bond will come here. So it would give you a peroxide. Okay, so aldehydes also actually benzaldehyde, mostly benzaldehyde, that gets easily oxidized to benzoic acid. So when in the laboratory we just say, okay, you have to do the tests, like first you do acidic test, then you do the test actually stepwise. But you have benzaldehyde, but you would it will show that you have acid is present, carboxylic acid is present. The reason is, once the benzaldehyde bottle gets opened, it some of benzaldehyde gets oxidized to your benzoic acid. So more the time your benzaldehyde, means the bottom like the bottle cap is open for a longer time, then there would be more amount of or larger concentration of your benzoic acid. So benzaldehyde actually gives you benzoyl radical, which in presence of oxygen gives your porbenzoate radical. So this porbenzoate radical again abstracts one proton from your aldehyde to give you porbenzoic acid and your acyl benzoyl radical. Okay, so finally that would give you your benzoic acid. Oxidation with lead tetraacetate. In presence of lead tetraacetate, actually we know that our diols, in presence of lead tetraacetate, they undergo oxidative cleavage. Actually, this is known as your diols oxidative cleavage in presence with lead tetraacetate. So first lead tetraacetate actually gives you lead diacetate plus two acetoxy ions. So the acetoxy radicals, sorry. These acetoxy radicals generate actually abstracts hydrogen radical from this, giving you di radical, which again goes on bond cleaving, that is your oxidative cleavage, to give you your ketones. Okay, so in this case, as you know that oxidative cleavage is fast, actually cleaved considerably in your cis diols as compared to your trans isomer. Okay, next comes your rearrangement reactions. These radicals also undergo rearrangement. Like in case of carbocations, we know that they undergo rearrangement. In this case also, they undergo rearrangement whenever there is any possibility. Just see this radical which is being formed from the removal of carbon monoxide. So this radical gets stabilized by this aranium ion, which so now you have a like three centered cyclic intermediate, so which again goes back to your this carbon. Like first it was on this carbon, the phenyl group. So because of this radical rearrangement, it has gone to your carbon number 2. First it was on carbon number 1, then it has been migrated or shifted to carbon number 2. And so it when in migration is there, most of the time aryl group is uh, migrates. That means migratory aptitude of aryl group is more as compared to your methyl group. Then comes your radical ions. Radical ions means you have a negative charge as well as a radical. So you have two type of radical ions. You can have radical anions or you can have radical cations. So in case of radical anions, suppose you just see this hydroquinol, this hydroquinol. So in this hydroquinol, in presence of your OH minus, one electron is removed from, one electron is given to this one, and one hydrogen is being removed from this one. So you have a radical as well as a anion. So this one is resonance stabilized in this way, and finally that would give you hydroquinone plus quinone. Okay, that is radical anion. And in case of radical cation, when you remove one electron from this nitrogen, okay, so you get, means now this nitrogen is electron deficient, so that would be N plus and dot. And this one is also resonance stabilized. How you do it? You do it like this, and this one will form a bond here. You get a radical here. Again, it goes on to give you this kind of resonance. So that is stabilized by resonance. So these are your radical ions. So that's for your free radical as an intermediate. Next is your carbons as intermediate. Up to now we have carbocations, carbanions, and carbon and free radical. In all the cases we have carbon bonded to three groups, and it can have a positive charge, negative charge, or a free radical. But in case of carbon, it is attached to two groups, and it has a pair of electron. This electron, two electrons, it can be in a lone pair, as a lone pair, or unpaired. Okay, paired or unpaired. Okay, what are the generation, means what are the nomenclature name actually? This is your methylene carbene, this is dichlorocarbene, this is diphenyl carbene, or so. So this dimethyl carbene are in your trimethyl boron. As you can see, they are isoelectronic because the number of electrons are the same. Okay, and this is also have a 6 electron in its valence shell. Carbon is having 6 electrons in its valence shell, and this one is also having 6 electron in its valence shell. So these two are actually acts as your Lewis acids, or these are also electrophiles because they have incomplete octet. But sometimes you will see in very less number of reactions, carbons act as an nucleophile, but mostly it acts as an electrophile because its octet is not complete. It has 6 electrons in its valence shell. So how these carbons are generated? First one is your photolysis or thermolysis of diazomethane. So this diazomethane, when in light or heating, it just undergoes thermolysis to give you a very stable living group. Actually, you will see that this kind of happens whenever you have a group which is after living, which is very stable. Here we have nitrogen, here we have carbon monoxide. These are gases, so these are highly stable molecules. So you get actually your carbons or this type of intermediates whenever that is adjacent to a highly to a group which has more aptitude, or which is a better living group. Okay, from haloalkanes. So when we treat our suppose chloroform with potassium tertiary butoxide, that is a base, strong base, so that would remove this proton because we have this proton is acidic. You cannot remove this proton from actually from methane, but this proton is acidic because of the presence of three chlorine groups which are more electronegative. Okay, it has electronegative groups. So this proton is acidic, that can be removed by a base to give you first CCl3 CCl3, then that goes on to give you dichlorocarbon. Even you can use n-butyl lithium also. Okay, from methylene iodide, you just see this is known as your Simmons-Smith reaction, in which your methylene iodide reacts with zinc in presence of copper or silver to give iodomethyl zinc iodide, which again gets cleaved to give you methylene and zinc iodide. Next is your thermal decomposition of sodium trihaloacetates. So this trihaloacetates gets decomposed, you have a very good living group carbon dioxide, that is also known as your decarboxylation, to give you sodium, actually uh, okay, so that gives you Na plus CCl3 minus, which again your sodium chloride is removed to give you dichlorocarbon. Okay, so even from para-toluene sulfonyl hydrogens and of aldehydes and ketones also you would get your carbon. So there are number of methods, number of ways in which you can generate your carbons. Okay. There are so many methods. One is your that is your tetrazole. You just see tetrazole. It is a ring compound. Only one is carbon. The other four are your nitrogen containing compounds. So this undergoes a kind of bond breaking in a concerted manner to give you this compound, which again actually gets rearranged to give another molecule of nitrogen to give your carbon. And this ylide, from ylides also you get your carbon, because this one would be easily removed to give you dimethyl sulfide, and you get your carbon. Next is comes your structure and stability of carbons. So in this case actually carbon, uh, we have two in total carbons we have four electrons on carbon, two are being involved in bond formation and two electrons are there. So either it can undergo sp2 hybridization or sp hybridization. As you are having two bonds, it can either go sp or sp2. When it is undergoes sp2 hybridization, it has the in case of both the electrons will go to your sp2 hybrid orbitals and p orbital will remain empty. But in case of your carbon which undergoes your sp hybridization, so two p orbitals remain there. So as they are degenerate, both the electrons, like every orbital will have one electron. So in this case, this is known as your singlet carbon and this one is known as your triplet carbon. The reason is in this both the electrons are remaining in the same orbital. So here the actually its multiplicity is 1, because that is 2s plus 1 your multiplicity. So you have plus half and minus half, so s is equal to 0 in this case, and in this case it is plus half both will be of the same spin, plus half and plus half, Hund's rule of maximum multiplicity. So that would be 2 into 1 plus 1, so that would be equal to your s is equal to 1, and the small s, then the spin multiplicity capital S would be equal to 3. So that's why this is known as your triplet carbon, this one is your singlet carbon. If you just say triplet carbon is more stable as compared to your singlet carbon, the reason is in this case you have electronic repulsion as both the electrons are remaining in the same orbital, and in this case there you are having like both the electrons are remaining in different orbitals in degenerate orbitals. Actually what happens that sometimes your triplet carbon is always in the ground state, but uh, uh, it gets interconverted to your singlet carbon also in the reaction medium. So singlet carbons, actually your carbons get stabilized when you have a presence of a group or atom which is having unpaired of electrons. Similarly, this is stabilized by your phenyl groups also. Next comes your reactions of carbons. It can have undergo addition reactions, insertion reactions, or rearrangement reactions. So addition means it is being added to a compound. Insertion means it is being inserted between a bond. As you can just see, in between this carbon and hydrogen bond, this CH2 carbon, methylene carbon has been inserted, and rearrangement we know that one group is must be migrating. So we will study one these reactions one by one. So first is your cycloaddition reactions of carbons. So this carbon, our dibromomethylene carbon, when it is added to trans 2 butene, it gives you trans dimethyl dibromocyclopropane, and when added to your cis 2 butene, that gives you cis dimethyl dibromocyclopropane. So this is quite stereospecific. Okay, when you just do this reaction in the presence of an inert gas, as you see here, here you have a singlet carbon. Okay, so the both are being added from the same side. So when it is carried out in the presence of an inert gas, the carbon gets converted to your triplet carbon. So first, as it is your singlet carbon, triplet carbon is reacting. So now this is of up spin, this is of off spin. So now these two won't react. So in that case, what happens, either there would be spin inversion to give you the same cis one, or it can invert, the rotation can take place along this way, so that there would be within that time your this bond is rotated and again spin inversion, so that you would get a trans product. So either singlet carbon can react, or in the presence of an adjunct gas, that gives you triplet. So in that case, you are getting a mixture of cis and trans. Okay. Even your syn addition of your carbon to a cyclohexane gives a bicyclic product, and both will be attacked from your same side, giving you cis bicyclo uh, bicyclic product. Cis means it is like both the hydrogens are on the same side and they are on the same side. So when it reacts with actually pyrrole, in that case you get a ring expansion. So you see, first it gives you this pyrrole, this hydrogen actually that is acidic, so that gives you this pyrrole anion. So now that reacts with your carbon dichlorocarbon, as in actually it goes here, addition here. So you get a bicyclic ring here, but you have a negative charge here, so that ring opens. So from 5-member ring to you are getting a 6-member ring. So this is a very good method of reaction from the synthesis of pyridine from pyrrole. Insertion reactions of carbon, as I have already told, these carbons can be inserted in between two atoms of a bond. So here in the methane molecule, the bond in between carbon and hydrogen, this carbon is being inserted to give you ethane. So similarly, you can get these reactions also, like in case of your propane that is being inserted and you get a butane. And this insertion can go either, actually you see we have alpha hydrogen, or we have primary hydrogens, or well as your secondary hydrogens. It can insert either along your primary carbon hydrogen bond, or secondary carbon hydrogen bond. So that will give you different a mixture of products. And in case of your insertion in a stereoregular compound, in that case it can actually, this insertion leads to an inversion in configuration. As you can see here, because of the inversion, first this hydrogen and OSU, where acetate group were on the same side, but after insertion of this carbon hydrogen bond, you see this acetate and this acetate are on the same side, but previously this acetate group and this acetate group were on the opposite sides. Okay. So you have different type of insertions, and in this insertion also you just see there is increase in your ring size, expansion of your ring size occurs. So there are a lot of slides. Next comes your rearrangement of carbons. So when carbons okay, we have this carbon. So next what happens, this carbon, okay, from this diazoacetate, this one will be rearranged to this one, and you get a ketene, phenyl ketene. Now this phenyl ketene react with water to give you phenylacetic acid, or ester when it is reacted with alcohol, or with ammonia to give you an amide. So this reaction is actually your Wolff rearrangement. So mostly your diazo compounds, diazoacetophenone, when treated with silver oxide, first it generates your carbene which undergoes your rearrangement to give you phenylketone. Even this reaction undergoes in ring contraction also. Suppose you just see this cyclic bicyclic product diazoketone. So this undergoes first step is the generation of carbene. Okay, first step it here hydrogen should not be here. This nitrogen cannot be 5 bonded, means its bonding can be only up to 4. So that will come here. No, not like this. So first this one will be like this. So next this will come here and this bond will go, so you have a carbon intermediate. Now this carbon intermediate will undergo rearrangement like this, so that your this one will go here and this one will be migrated to this side. So this carbon now is attached to this carbon and this carbon is bonded to, so this one is suppose 1 2 and 3. Now there is our, this one is our 1, this one is 3, this one is 2. So that gives you ring contraction. So often reaction with alcohol, that gives you an ester. So next is your Emer-Tiemann reaction, which involves the formation of your salicylaldehyde. Uh, Okay, so first step is the from chloroform in presence of potassium hydroxide, that gives you dichlorocarbon, and this as this is it being done in your alkaline medium, the first it generates a phenoxide, which undergoes actually kind of electrophilic substitution reaction to generate this intermediate, which often many reactions that gives you salicylaldehyde. Next is your carbyl-amine reaction, which is mostly done to distinguish between your primary, secondary, and tertiary amines. Most primary amines actually gives a response to this test, and that gives you a very foul smell. So from that you can just say that whether you are having a primary amine or secondary tertiary. So primary amine mostly gives you this test, secondary and tertiary amine doesn't respond to this test. So what happens here also, first is the formation of your dichlorocarbon, which is in presence of your primary amine, that gives this kind of this undergoes this type of reactions, which finally gives you an isocyanate, which have a foul smell. But whenever in case of secondary and tertiary amines, you do not have the presence of these hydrogens, so this elimination cannot occur to give you this isocyanate. So secondary and tertiary amines does not respond to this reaction. Next is your Wittig reaction. So when triphenyl phosphine is treated with dichlorocarbon, that gives you an halide. So when this halide is treated with your actually a carbonyl compound, finally you get a car- carbon-carbon double bond. Okay, so it undergoes a kind of this is a dipolar reaction, so that undergoes a four-membered ring, which again undergoes bond cleavage in a concerted manner to, as oxygen and phosphorus has more affinity for oxygen, so that gives you a um, phosphorus oxide and carbon-carbon double bond is formed. Actually, this Wittig reaction is a very good method to increase the carbon chain by any number if you want. So that would be carbon-carbon double bond. You can have any. So that is being converted. So that is your Wittig reaction. Next comes your nitrogen as intermediate. So till now, any doubt? Any doubt? Shall we take a break or we will continue?
Ma'am, continue.
Continue. Okay, I will be back in 1 minute. Okay, you just stay.
Ma'am, muted Ochi call.
Okay. So now we will talk about nitrins as your intermediates. So in nitrins, this is just like your carbons. So here we have a one group attached to it, one lone pair of electron which is already on your nitrogen, and there is another lone pair of electron. Okay, so which is actually reactive. This pair of electrons are reactive, these are not reactive. So this is, we can count them as your lone pairs. Okay, so how these are generated? This can be generated from hydrazoic acids, HN3, by the removal of nitrogen. It gives you this nitrins, and these are alkyl nitrins. When we treat it with uh, the azides in presence of light or your uh, actually thermal decomposition, that gives you nitrins, and nitrogen group is nitrogen gas is released here. So most of the things you just see in case of free radicals, carbons or nitrins, for generation we are either using light or thermal process, because these molecules are not very stable. So in presence of light or something, we are generating this intermediate, and again we are just using it in our reactions. So these are generated in situ and we are using it in our reactions. Okay, and so like this alkyl azide, that is resonance stabilized to give this kind of uh, compound, and that is that structure, and again removal of nitrogen gives you your nitrins. So there are, most of these are having the same type of mechanism. So here mostly in presence of your light or thermal decomposition, you get your nitrins. Okay, so in this case also, that is your tri benzene azide, benzyl azide. So you just see in this case, as soon as this as a nitrine is being formed, that immediately actually gets added to this benzene ring. So and then you can attack it through your aniline, and ring expansion occurs. So this one actually, it would be like this. So this would first give you a bicyclic product. So now this uh, actually aniline, nitrogen is your nucleophilic center that will attack at this carbon, and ring expansion occurs to give you a seven-membered ring. Also from your oxidation reduction reaction, as we have done in case for free radicals, also you can get your nitrins from isocyanates. From isocyanates in that is also a intermediate actually, you will see, or we generate this compound in which in our reactions mostly. I think you might have seen it in your Hofmann bromamide degradation, which we will later on also do, but that is I think from BSc level we have that Hofmann bromamide reaction, and this isocyanate kind of intermediate we are having. So this also, when this isocyanate is treated in presence of or it is exposed to light or thermal heat it, then that also gives you your nitrine. Okay, we have different processes. We won't go through it more. So we, what is the structure and stability of nitrins? Like your carbons, this nitrine is also of two types. We can have singlet nitrine or triplet nitrines. The from electron spin resonance studies, actually it was seen that triplet nitrine is your ground state level. Okay, that is of lower energy as compared to your singlet nitrins. So reactions of nitrins. So first reaction is your isomerization reaction. As you can see that this hydrogen is being removed by this one to give you an imide, and also by hydrogen abstraction from any other medium. Okay, if we have something other medium or any alcohol or anything that would abstract hydrogen from it to give you an amine. This is imine and this is amine. Al- Alkynyl nitrines generally rearrange to imines which are tautomeric with your nitriles. When you have a alkynyl nitrine, that means you have a double bond, which is your the nitrogen is attached to this carbon and this carbon is having a double bond. So this is your alkynyl nitrines. So what happens? This alkynyl nitrines actually rearrange. So this hydrogen will go here and this will come here. You have your this hydrogen will go here. So that first rearrange to give your imines, and which is tautomeric with your nitriles, because that would be more stable form. So this is your tautomerism. That means in your reaction mixture you may have a mixture of this, that is, they will be always in equilibrium with each other. Tautomerism is not your resonance, but this is just the you are having two different uh, type of compounds in the same in the same mixture. Actually, by the you're here only the uh, position of hydrogen is changed. So previously it was with nitrogen and here it is with your carbon. So that is known as your tautomordism. So they are always in equilibrium with each other, like your keto-enol tautomordism. You can either remain in your keto form or enol forms. Then it can undergo dimerization. Two nitrines can dimerize with each other to give a diazo compound. Okay, or it can do your hydrogen abstraction, like in case of your carbines, it can abstract one hydrogen from other uh, group to give you one, and in this case your primary amine. Okay, and such as you just see this azido format, the in situ gives you this uh, nitrine intermediate, which again takes out some proton or hydrogen abstracts from your solvent or something to give your alkyl carbamate. Next is your insertion reaction, like carbene will be inserted in between two bonds to give you one secondary amine. So that is your insertion reaction. Like here, this carbon hydrogen bond, in between this carbon hydrogen bond, this carbene is this nitrogen is inserted to give you one secondary amine. It can either inserted on this carbon hydrogen bond on this one, but it is being seen that this one is having your major product. Sometimes your nitrogen insertion in a carbon hydrogen bond leads to ring closure. As you just see, this will give you a nitrogen. Okay, so now this nitrogen will be inserted between this carbon hydrogen bond. So that would go here. Okay, so now that would give you a ring closure. Okay. And so when this react with your cis 1,2 dimethyl cyclohexane, so this is also a your insertion reaction. If you are using your singlet, mostly your nitrines, that gives you your cis product. Okay, both the groups they remain the same, just it is being inserted in carbon hydrogen bond. And in case of a trans, so the geometry does not change. Like the in the initial condition, your both the CH3 groups are on the same side, and in the product also both the CH3 groups are on the same side. So here in case of trans, CH3 groups are on opposite side, and in the product also your CH3 groups are on opposite sides. Next is your 1,3 dipolar cycloaddition. So these are your 1,3 dipolar compounds. So this actually 1,3 dipolar because uh, this negative charge, as you see, this charge is being spread between 1 and 3 positions. Okay, so that is your 1,3, and this is two charges plus and minus in case of ozone, although it is neutral, but this is its structure. Uh, so that is a 1,3 dipolar compound. So when these nitrines react with 1,3 dipolar compounds, that undergoes your acid. Okay, cycloaddition system that gives you a that undergoes 1,3 dipolar cycloaddition. Okay, so this nitrine when reacts with this carbon nitrogen triple bond, so that undergoes one cyclization to give you 1,3,4 oxadiazole. Okay, addition to alkanes. When these nitrines are added to alkanes, that the cis gives you the cis, and the trans also cis and trans, and the trans butene also gives you a mixture of trans and cis. The reason is actually it can go with either singlet nitrine or triplet nitrine. So with singlet nitrine, actually in case of cis 2 butene, mostly uh, it gives it gives you stereospecific product. So some of this will give you a cis product, but if the system or if the reaction medium permits, some of will be converted to your triplet carbene. So in that case you would get a trans product. Next comes your rearrangement reactions of nitrine. In case of rearrangement reaction, mostly you will see that there is 1,2 alkyl shift. Means the position, if this is 1, this is carbon number 2. So the group which is present at carbon number 2, that will be shifted to nitrogen. So that is your 1,2 alkyl shift. So mostly you will see this kind of rearrangement reactions in case of your nitrines. So first one is your Hofmann-Bromamide reaction. Okay, in case of your Hofmann-Bromamide reaction, also known as your Hofmann rearrangement. So in this one, from your amide, you are getting a primary alkane, a primary amine with one carbon atom less. So what happens here in presence of actually alkali, that first generates this uh, a negative charge, like this takes out this proton, and so we get this anion. So this anion uh, then gives you this n-bromo amide. Then it again takes out the proton from here, generating your nitrine. Okay, so now this nitrine undergoes rearrangement to give you isocyanate. Okay, so that would go here, and that would give you isocyanate. So now this isocyanate is reacted with water to give you the your this acid, and which upon decarboxylation gives you primary amine. And in case of your Cortius rearrangement, your acyl halides, which you can just get it from your carboxylic acids. So first you treat it with uh, potassium azide. Potassium azide would give you your acyl azide. So now this acyl azide undergoes actually fragmentation to generate your nitrine, and this nitrine intermediate undergoes rearrangement to give you isocyanate. So you just see in Hofmann rearrangement as well as in Cortius rearrangement, you are getting a isocyanate. So this isocyanate, depending on your reaction condition, will give you different products. If you react it with alcohol, then you get an esteramide, and if you treat it with water, then finally you would get an amine, and if you treat it with secondary amine, you would get an amide of this kind. Next is your schemate rearrangement. In schemate rearrangement, this also goes through your isocyanate intermediate. Okay, so this isocyanate intermediate, when treats with water, then finally you are getting your amine. So you have to actually remember all this mechanism. So how it happens? So first of all, acid, when treated with a stronger acid, actually that should be a stronger acid as compared to carboxylic acid, it gets protonated. Then water is removed to give you acylium ion. So this acylium ion is stabilized by resonance, and you treat it with uh, hydrazoic acid. Okay, hydrazoic acid to give you acyl azide. So this acyl azide, when you heat it, nitrogen gas is removed to give you isocyanate intermediate. Okay, so this would go here, and this will be expelled. Nitrogen gas will be expelled. So now in presence of water, then water molecule will attack this carbonyl carbon, and you get this compound. Then again this proton will be lost, you would get this one, and this nitrogen will take out that proton to get this ammonium ion. Next step, this proton will again be lost to give you this carboxylate, which will get decarboxylated to give you RNH2. Carbon dioxide will be removed. So in case of your Huffman and Curtius rearrangement, as you see, from amide, you are getting one isocyanate intermediate, and with the reaction of water, it gives you your primary amine by the loss of carbon dioxide. And in case of Curtius rearrangement, the first one is your acyl azide, which you get it from your acyl halide. Okay, acyl halide to acyl azide. Again, that would go give you isocyanate, which is an intermediate, and depending on the reaction condition, you can get the product. If you are using ROH, then you are going to get your carbamate. So in every rearrangement, this one is the key step in which the first is the formation of your nitrine intermediate, then your 1,2 alkyl shift, and this leaving group is departing, generating your isocyanate intermediate. Then attack of nucleophile to give the respective product, whatever is the nucleophile. So that is your nitrine as intermediate. Next comes your arines as intermediate. I think in your BSc, you must have studied aromatic nucleophilic substitution reactions. There are actually uh, in aromatic nucleophilic substitution, you have addition elimination mechanism, elimination addition mechanism, and another one is your okay, this goes through these two mechanisms. I forgot the other one, I will check. But okay, here you see this chlorobenzene, actually aliphatic amine is aliphatic halides. Okay, alkyl halides are easier for nucleophilic substitution as compared to aryl halides, because in case of your aryl halides, okay, we know that SN1 and SN2 in, okay, whatever group it is, in SN1 first we remove this group to generate a carbocation species. Okay, and then nucleophile attacks, and in case of SN2, nucleophile attacks from the backside and the leaving group departs. So SN1 and SN2 does not happen in case of your aryl halides. The reason is it is difficult to break this bond because this acquires a double bond character. Because the lone pair of electron on this halogen actually uh, gets delocalized onto this benzene ring. So this acquires a double bond character in case of your aryl halides. So this is difficult to break this bond. Again, for SN2 reaction, you have to attack it from the backside, but it has to go through this ring current. So SN1 is not possible, as well as SN2 is not possible. So what happens is it goes through some mechanism. We will deal with it, but in this case, the reactions proceeds very smoothly. As you can just see here, when we use chlorobenzene, we have to use 625 degree Kelvin, so high temperature and so high pressure, it gives you this product. And when we are using a very strong nucleophile, that is your amide NH2 minus in liquid ammonia, then that gives you the product. But when we replace it in the ortho and para position, when we put two highly electronegative groups, that is nitro groups, the reaction proceeds smoother. Like when we put three electronegative groups at ortho and para position, only water, you don't require any strong nucleophile also, only in water, just heating condition, that gives you the product. And also liquid ammonia also gives you the product. Liquid ammonia is not a very good nucleophile, because here you have a very strong nucleophile NH2 minus, so this is NH3 is actually neutral, so not a very good nucleophile. But in this case, the rate of reaction proceeds very high. And in case of when you have already not an electron withdrawing group, but you have a electron donating group, CH3 group here, but these reactions proceeds very smoothly in liquid ammonia in presence of NH2 minus, but it gives you two different products. Okay, the same in this case also when you are using aqueous sodium hydroxide and heat it. So these three pass, okay, these two pass through different mechanism, that is your addition elimination mechanism. That means the nucleophile first attacks, then is eliminated. So that attack is actually enhanced by the presence of your nitro groups, electron withdrawing groups, specifically at your ortho and para positions. But what about this reaction and this two, A and D? So this goes through actually a different mechanism, that is your elimination addition mechanism, or that is known as your benzene, through benzene intermediate. So what happens here, actually this hydrogen which is present uh, alpha to your halogen group gets removed, but you can just see in these cases we are using very strong bases, so that can abstract a proton from this hydrogen, and in this case we are using very strong condition also. Although aqueous sodium hydroxide we are taking, but we are uh, doing this reaction at very harsh conditions. So this hydrogen which is present alpha to it, although not very acidic, but we are using a very strong base to remove this proton, and first elimination occurs, then you're forming a benzene intermediate which now can react at both the sides, either on this curve or on this side, resulting in the formation of two products. And these two products are actually, you can see, they are almost of equal concentration. So we will actually mm, learn about it later, but in this case that is known as your elimination addition mechanism. Because in the first step elimination occurs, and in the next step your addition occurs. So what is the generation of your benzenes? How benzenes are generated? From orthoaminobenzoic acid. So when orthoaminobenzoic acid is treated with nitrous acid, first it is forming a diazonium salt. So this diazonium salt, actually this diazonium salt is very actually not very stable, so it immediately releases nitrogen, forming a carbocation which is immediately actually undergoes decarboxylation to generate your benzene. And from aryl halides also, as we have already discussed, so this hydrogen is acidic in presence of a strong base that would take out this proton, and this would be eliminated. Okay, this hydrogen will be removed. So that is the kind of elimination mechanism. So even from iodophenyl mercuric iodide also, when you do the flash photolysis, that also generates your benzene. So this iodide would be coming here. Okay, so even from 1,2-dihalobenzene, when we are having 1,2-dihalobenzene, suppose 1,2-bromofluorobenzene by the formation of Grignard reagent. So when we have a actually dihalo compound, mostly 1,2-dihalo, and bromine will form better bond with metals as compared to, or form better organometallic reagent with your metals. So we can just use these metals, sodium, magnesium, lithium, or copper, to form a organometallic reagent, which again can undergo like this type of reaction, magnesium. So you see this magnesium, when you use magnesium, actually this has to be done in very dry condition. In presence of magnesium, it first generates this organ metallic compound, that is your Grignard reagent, and then it undergoes your elimination to give your benzene. Even lithium and copper can also be used, but sodium is more reactive. So it's better, we most of the time you can see we use magnesium. Okay, there are different methods also. LDA is your nothing but a base, lithium diisopropylamide, that is also a base. So this base is very strong base, so this can remove this proton, so that you get this kind of reaction. And in this case also, first would be the formation of N2 plus, your diazonium compound. So now this diazonium compound can form a ring compound, which again can be decomposed to give your benzene intermediate. Next comes your structure and stability of benzene. So benzene is like in benzene we all know that all the carbon atoms are sp2 hybridized. Okay, so the sp2 hybridized carbon atoms are bonded to one hydrogen and two carbons on their side. Okay, so this sp2 carbon is bond, and the pi electrons are delocalized onto this p orbitals. So when we are putting another bond between here, actually in case of alkynes, this carbon is sp hybridized. Okay, this carbon is sp hybridized, and here the bond angle is 180 degree. So in this case, actually, when as it is alkyne, and this one is named as benzyne, because you are having carbon carbon triple bond. But here, as we know that in case of your carbon carbon triple bond in alkynes, there is pp bond. Actually, the pi bond is formed from the p orbitals, okay, by the overlapping of your p orbital, mutually perpendicular p orbital. But in this case, one p orbital is already actually overlapping with the other p orbitals of other carbon, but the sp2 orbitals are now there for your overlapping. Actually, there is no pure p orbitals for alkyne. So this is kind of, actually, benzyne intermediate is kind of actually very unstable, because sp2 overlapping is not very strong. Actually, for overlapping, this should be parallel to each other, and this is, the angle is not perfect actually. So and actually this, because sp2 orbitals are 120 degree to each other, so they are not good for your sp2 overlap, but still there is a double bond between them. Or rather, you can just say that there is a poor actually dipolar character, like one orbital is having positive charge, other orbital is having negative charge, which dwells on actually negative double triple bond and again dipolar character. So you can just say that although you are having a triple bond here, but still it acts as an electrophile, because it is having a very low energy LUMO. This is not very stable, and again this is having a very low energy LUMO, which can actually have a lower energy barrier for the HOMO of the nucleophile to attack it. So it is the LUMO of your um benzyne intermediate, and the nucleophile HOMO is very nearer to it, so it can attack it. So that's why this acts as an electrophile. And it's for this one to act as an uh, nucleophile, its HOMO is very far down, so it can actually act as a electrophile. Next is your reactions of arynes. So what are the orientation? First we have to see, like you see, when you have a substituent here and your halogen is already here, so there is no possibility, only this hydrogen will be removed to give you this uh, benzyne. Even when you have a para substituted product also, either this hydrogen or this hydrogen can be removed to give you this benzyne. But when you have a meta substituted product, then you have a hydrogen at this side and hydrogen at this side. So in that case, if this one is being removed, then you are getting, suppose this one is 1, so you are getting this benzyne, or when this hydrogen 2 is removed, you are getting this benzyne. So in that case, which one will be removed? Actually, the more acidic hydrogen will be removed. The more acidic hydrogen will be removed. So if you have an electron withdrawing group here, then this hydrogen will be more acidic. So in that case, this hydrogen will be removed, not this hydrogen. Okay. Here it is saying electron attracting. I am just saying electron withdrawing. Okay, electron attract. It can attract electron or it can withdraw electron from the group. So when you have a electron withdrawing group or attracting group, in that case this hydrogen will be removed, and when you have an electron donating group, then this hydrogen will be removed. Okay, so next is, what would be the stability of the carbanion formed? Actually, once your this hydrogen is removed, okay, so now the addition, when addition occurs, then first it can either attack this position or it can attack your this position. So this leads to two carbanions here. So if it attacks, suppose in this case, okay, we do not have any problem because both the positions are same, it can give up. So what is the, okay, here one thing, what is the actually evidence that this type of intermediate is happening? Suppose you just one of the carbon you have taken carbon 14 isotope, others are your carbon 12 isotopes, so that is your isotopic study. So when this chlorobenzene was studied, when where one carbon is isotopically labeled, then you can find that there is a mixture of two uh, anilines, where in one aniline the amino group is attached to the labeled carbon, in another that is just present adjacent to the carbon where there is no label. So you get a mixture of two. So there cannot be any other type of reaction in which you would get a mixture of, and that would be equal mixtures. So you cannot get any other mechanism or which can actually explain this one. Again, in this case, you just see when you add, okay, this is the only hydrogen can be removed either this from this side or this side, giving you this benzene intermediate. So now this amide can either attack this side or it can attack this side. Okay, when it attack this side, resulting in your metatoluidine, and when it attacks this side, it results in your paratoluidine. So it depends on the stability of the carbanion intermediate formed also. So in this case, as it is an electron donating group, okay, as it is an electron donating group, and here mostly actually here inductive effect will come into pronouns, because here we are not, this does not take part in delocalization, this negative charge. Okay, this negative charge doesn't take part in delocalization, so only inductive effect would be the uh, mm, uh, final decision that will also only take the final decision. So in this case, as we are having a electron donating group, so this one will be less stable as compared to this one. So this one would be metatoluidine, would be your preferred product as compared to your paratoluidine. Suppose in this case, you see, we have orthobromoanisole. So when first this forms this 2,3 benzene, now this 2,3 benzene, okay, we can have only this product only. Okay, this is your 2,3 benzene, but when we have a meta substituted, so you have a hydrogen here and you have a hydrogen here. So either this hydrogen can be removed to get you this type of benzene, so this could have given you this type of benzene, but this won't be happening because this hydrogen is more acidic, because OCH3 group is a electron withdrawing group, minus I group. So this hydrogen is more acidic as compared to this hydrogen. So this is the only product you are getting. So now again, when you add NH2 minus, so now it can either go to this carbon or this carbon. So if it goes to this carbon, the negative charge, the carbanion will be generated at this carbon, or if it attacks this carbon, then negative charge will be delocalized onto this carbon. So as you have a negative charge next to your electron withdrawing group, so this one is more stable, this one would be less stable. So in that case, this one would be your product, major product. So another evidence is that when there is no hydrogens present in your ortho position, no reaction will occur. Okay, there would be no reaction. Even the rate of reaction would be slower when you put a deuterated instead of at the alpha position, you, instead of hydrogen, if you put a deuterium. So in that case, because our in this reaction carbon hydrogen bond breaking is taken place, like that is the slow step. So in that case, your kh is much higher as compared to your kd, that is the equilibrium reaction constant, rate constant for hydrogen carbon hydrogen bond. The carbon hydrogen bond breaking is more as compared to your carbon deuterium bond breaking. So that also signifies that this kind of mechanism is going on. Okay, when the reaction means the substituent is coming to the same place where your living group was there, that is your same substitution, but when it is going to other position, that is known as your sign substitution, sign substitution. Next comes your cycloaddition and ring closure reactions. So this also gives a very good method for the uh, synthesis of cyclic system. As you see here, you have your hydrogen. So in presence of an base, that would be removed, this acidic hydrogen, generate the carbanion, so which, or we can just write it like this, the chlorine will go, that gives your benzene intermediate. So now this benzene intermediate will be attacked by the actually intramolecular. Okay, there is a nitrogen already present in the molecule that will attack here to give you a bicyclic product. Similarly, in this case, in presence of lithium and mercury, so first that would form a lithium bromide, and then organometallic, and then that would be removed to give you your benzene intermediate. So now this can undergo 4 plus 2 cycloaddition reaction. So this acts as a dienophile, and this acts as your diene. Okay, dienophile reaction, if you know that, that is a cycloaddition reaction plus this one. So that happens in a concerted manner. So that gives you a cyclized product. So in this case, you don't have to worry about whatever groups are there, but actually this is 1, 2, and this is your 3, 4, 5, 6. Just you add here, it will go there, then it will add here. So the oxygen containing carbon, one carbon is coming here, one carbon is coming here, and this is your this bond 4 and 5, 4, 5. This is your okay, 4, 5. This is your 3, and this carbon is 6. I have given this 1 and 2. So this is a kind of 4 plus 2 cycloaddition reaction. Similarly, you can just see that 1, 2, 3, 4, 5, 6. So you will form a bond between 1, 2, 3, 6. So that would give you a this type of tryptophan. So that is actually cycloaddition reaction, or sometimes that is used, this anthracene is also used to trap your benzene. Okay, that also undergoes dimerization, like two benzenes undergo dimerization like this, 2 plus 2 cycloaddition, that gives a cyclobutane, or trimerization, like in alkynes. As you all know, alkynes give you your benzene. Okay, that gives you benzene. So it goes on like that. That also undergoes 2 plus 2 cycloaddition with another dienophile. This is dienophile, this is also dienophile, but this undergoes addition reaction, 2 plus 2 cycloaddition reaction, to give a 4-membered ring. In this case, actually, if you just see, this is not 1, 2 plus 2, this OH group reacts here, and this attacks this nitrogen. Okay, so this nitrogen and this comes here, so that gives you this cyclic product, attacks this carbon. Okay, not other. So this phenyl group which is there, but just you have the reaction 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, and in the 5 carbon you have a phenyl ring attached to it. So this finishes actually all of your reactive intermediates. So if you have any doubt, just let me know. Otherwise, I will discuss some questions. I got your assignment questions actually while searching, but I could not find many questions related to your topic. Actually, I searched in Sambalpur University site and Utkal University site, their syllabus does not match to your syllabus. So their previous year questions also won't match actually. Okay. So we can actually your assignment questions. Shall we discuss that one? You
Yes,
have
yes,
assignment
madam. Yes,
questions.
madam. Yes, madam. Please
Okay.
discuss.
Okay. Up to now, you have any doubt? Whatever I discussed today. କିଛି ଡାଉଟ୍ ଅଛି କି ଆଜିର?
ମ୍ୟାଡ଼ାମ କଟିସ୍ ରିଆକ୍ସନ।
କୋଉଟା? କଟିୟସ୍ ରିଆରେଞ୍ଜମେଣ୍ଟ। ଆଚ୍ଛା, okay. So Courteous rearrangement, तमें प्रथमे acyl halide रो, this is a kind of nucleophilic addition elimination reaction. Okay, chloride will be eliminated, so you get your acyl azide. So this acyl azide again undergoes bond breaking to give you your nitrogen group will be eliminated to give you your nitrine intermediate. So this nitrine intermediate undergoes immediate rearrangement by your 1,2 alkyl shift. This one will be shifted this way, and the lone pair of electron that will come here. So you will generate a R is now bonded to nitrogen, and that nitrogen is bonded to carbon, and that would be carbon oxygen double bond. So that forms a isocyanate. So when this isocyanate reacts with water, that would give you primary amine, or when it is reacting with alcohol, that gives you carbamate or dicarbamate. So that is your Courteous rearrangement. Mostly in these rearrangements, first is the generation of your nitrine, and then that undergoes 1,2 alkyl shift to give you isocyanate. Then you have a series of reactions by nucleophilic addition reactions, okay, and eliminations. ବୁଝିପାରିଲ କି?
ଏଇଟା ଯୋଉ ଆଇସୋସାଇନାଇଡ୍ ଯୋଉ ଇଣ୍ଟରମିଡିଏଟ୍ ହେଲା ତା ପର ଷ୍ଟେପ୍ ବୋଧେ।
ୟା ପରେ ନା ତା ପୂର୍ବରୁ?
ହଁ
ହଁ,
ତା ପୂର୍ବଟା ଆଉ ତା ପରଟା।
ତା ପୂର୍ବ
ଏଇଟା ହଁ ଏଇଟା।
ଏଇଟା ତ
ଆଜ୍ଞା।
এই যে 1,2 alkyl shift କେମିତି ହଉଛି ଦେଖ, ଏଠି ଆମର ଅଛି R C double bond O, ଓକେ ଏଟା ଟିକେ ଇଏ ହେଇଗଲା। এটা ଅଛି N, ଆମର ଗୋଟେ lone pair of electron ଅଛି, ଆଉ ଗୋଟେ lone pair of electron ଅଛି, ଆମେ ତାକୁ show କରିବାନି, this lone pair of electron is reactive. So what happens here, 1,2 alkyl shift, ये तार bond pair of electron सहित R group टा एଠିକି ଯିବ, ଆଉ ये एଠିକି ଆସିଯିବ, okay, that forms your isocyanate. R ତା ପାଖରେ କିଏ ଲାଗିଛି ନାଇଟ୍ରୋଜେନ, ତା ପାଖରେ नाइट्रोजन सहित कार्बन रो डबल बॉन्ड हो गला, ता सहित ऑक्सीजन, ओके. So if you just number it 1 2 3, so this R group is now bonded to nitrogen. Carbon R रो बॉन्ड टा भांगी जाईची आ ता पाखरे नाही, so R N double bond C double bond O, so that is your 1,2 alkyl shift, okay. So once this is being formed, now जो भी nucleophile आसीबो that will attack this carbon, because this carbon is more positive, more electrophilic. जो भी nucleophile तमेरो ROH हो जहाँ भी हो, okay, that will attack here. So this bond will go, so that generates R N double bond C O minus, एठी तमरो OH लागिला, okay. And so next step आसीबो पुणी एठी OH2, suppose water लागिछि, OH2 plus थिबो, एठी तमर negative charge हेछि, so that nitrogen will take out that proton. You just see this one, okay, water attacks this carbonyl carbon, okay, so now this forms this one, so this H plus will be removed and would be taken out by this nitrogen RNH. Again this proton will be removed, RCOO minus ହେଇଯିବ, and that will give you your amine. ବୁଝିପାରିଲ ତ?
ଆଜ୍ଞା ମ୍ୟାଡ଼ାମ, ଠିକ ଅଛି।
ହଉ, ଆଉ କିଛି କାହାର ଡାଉଟ୍ ଅଛି ଯଦି? ମେକାନିଜମ ଗୁଡାକ ବହୁତ ପ୍ରାକ୍ଟିସ କରିବାକୁ ପଡିବ, କାରଣ ୱିଥ ମେକାନିଜମ ସେ ପଚାରିବ ରିଆକ୍ସନ୍ସ ଗୁଡାକ, ଏଇ ସବୁ ରିଆକ୍ସନ୍ସ ଗୁଡାକ, ଓକେ। ଯାହାର ଯଦି କିଛି ଡାଉଟ୍ ନାହିଁ ତାହେଲେ ମୁଁ ଗୋଟେ ଦିଟା କ୍ୱେଶ୍ଚିନ୍ ସବୁ ଡିସ୍କସ୍ କରୁଛି, ହେଲା, ନହେଲେ ଯାହାର ଡାଉଟ୍ ଅଛି ପରେ ପଚାରିବ, ମୁଁ କିଛି ଡିସ୍କସ୍ କରିଦିଏ କ୍ୱେଶ୍ଚିନ୍ ଗୁଡାକ, ଓକେ। ଏଇଟା ଗୋଟେ ତମର ଇଏରେ ଥିଲା, ଏଇ ବେଞ୍ଜାଇନ୍ ଉପରେ ନେଇକି, ତ ଦେଖ, write the predicted product and the corresponding intermediate in each of the following cases. So ଏଠି इंटरमीडिएट आसीबो तमरो ए हाइड्रोजन टा ही रिमूव होबो बेंजाइन रो एबे जेतु करैछि तेणु ए इंटरमीडिएट टा फॉर्म होबो ओके नेक्स्ट स्टेप रे either NH2 एठिक जाई पारे और एठिक जाई पारे actually NH2 will go to your meta position because in that case the carbanion will be here which is more stabilized by this electron withdrawing group and next step hela tamaro proton abstraction karibo se ammonia ru so that you would get your final product so this is going to be your only product it hydrogen rahijibo and in this case you have this hydrogen is more acidic so this is the only again this is the only possibility giving you that product and in this case you have the only possibility is uh, this hydrogen or the other hydrogen so you would get this benzene but in this case NH2 minus now can attack either this carbon or this carbon so if it attacks this carbon then you are getting NH2 here and negative charge here and chlorine or you would get NH2 here and negative charge here. So this is not stable, this is more stable. So that gives you the final product. Okay. So you can get तमर टर्मिनल क्वेश्चंस और सेल्फ असेसमेंट क्वेश्चंस बहुत गुड़े अच्छे से सब कर बुझी न पारे देखियो मत जदि मेसेज कर ओके नेक्स्ट है तुम असाइनमेंट क्वेश्चंस ओके 100 मार्क्स असाइनमेंट अच्छी मुझे जानी तुम के दिज्व तुम ये असाइनमेंट तुम इग्नू साइट रे गले मिल जाऊँगी ओके सबुथ्र मिल जाव तुमको केमिस्ट्री MCH एटा केते 012 ना कौन कि 102 012 तेणु तार अच्छी तुम इनऑर्गेनिक रो भी अच्छी बाकी जोतर भी सेगुड़ाकर सब अच्छी है तेणु से गुड़ा टिके चेक करदब आउ करने को चेष्टा कर तो देख first one name the two ways of representing three dimensional structures of molecules in two dimension तेणु फिशर रो आउ न्यूमैन रो हो सहर्स रो हो जोतरे भी करिवो हैला illustrate your answer माने न्यूमैन रे केमिति ताको रिप्रेजेंट करूची which one is your front carbon which one is your back carbon सेमति सब तमे लिखिबो ताको ओके एटा हैला प्रोजेक्शन फार्मूला उडा लिखिबो तापर नेक्स्ट होची कैरी आउट द फॉलोइंग कन्वर्जन्स ऑफ द स्ट्रक्चर गिवन इंडिकेटिंग द हां
मैडम सेडार एग्जांपल गोटे गोटे देले चलिबो ना
हां हां गोटे गोटे दबो किंतु तमे तांको बुझेबा को पड़िबो कोटा ऑन द प्लेन अछि कोटा बैक अछि हैला सेउडा सब बुझे के लिखिबो
ओके मैडम
हां आउ तार स्टैगर्ड फॉर्म तार एक्लिप्स्ड फॉर्म गुडा को मध्ये लिखिबो न्यूमैन आउ सहर्स जदी करूथबो ओके तापर नेक्स्ट देखो कन्वर्ट इनटू स्टैगर्ड न्यूमैन प्रोजेक्शन रे करिवो बट टू योर स्टैगर्ड कन्फर्मेशन रे करिवार अछि एटा ओके टू योर स्टैगर्ड कन्फर्मेशन को नबार अछि तो कोन करिवो आगो ताकू एटा जते बेले देखियो फिशर प्रोजेक्शन रे मोस्ट इट इज इन योर कोप फॉर्म में थाए सदा बेले सी एक्लिप्स्ड फॉर्म रे ही थाए तेन ताकू आगो चेष्टा करिवो ये कर दवा पई पड़ी करला ओके और एथ्रु मध्य चेक कर परिबो यार से स्टैगर्ड फॉर्म कहिस ना न्यूमैन पई मु ताको तार ये एक्लिप्स्ड फॉर्म रे अछि ओके तो एटा हला तमरो फ्रंट कार्बन मु ताको फ्रंट कार्बन रे एटा यार टिके तुम मैंने बहुत गुड़े प्रैक्टिस करले जानी परिबो हैला एटा हला हमरो फ्रंट कार्बन आउ एटा हला फ्रंट कार्बन तेणु यही फ्रंट कार्बन रो एटा हला हमर फिनाइल ओके तार लेफ्ट साइड रे अछि हाइड्रोजन एपर साइड रे हला क्लोरीन ए फिनाइल रो पाखरे एक्लिप्स स्ट्रक्चर रे ता पाखरे ऊपर कार्बन रो पछ कार्बन रो फिनाइल टाको इट लिखिलो ता पाखरे अछि ओके फिनाइल रो लेफ्ट साइड रे मिथॉक्सी अछि ओके ये पाखरे OMe आउ तार राइट साइड रे हाइड्रोजन अछि वर्तमान याकू 180 डिग्री रोटेट कर दबो ओके याकू जते 180 डिग्री रोटेट करिवो फ्रंट कार्बन को सेमिति रखिवो जेमति थिला तार सब्स्टिट्यूएंट PH एपटे Cl एपटे H आउ आरटा को रोटेट करिवो 180 डिग्री रोटेट कले ए फिनाइलटा आसीजिवो तमरो एठिकी एंड ए मिथॉक्सीटा तार जस्ट ऑपोजिट साइड OMe आउ ए हाइड्रोजनटा तार जस्ट ऑपोजिट साइड 180 डिग्री रोटेट कर सो दिस इज द स्टैगर्ड न्यूमैन प्रोजेक्शन सेमिति कन्वर्ट इनटू फिशर प्रोजेक्शन भी करि परिबो हेले तमे खाली ताको चेक कर नथुबो नेक्स्ट है एक्सप्लेन द स्टेबिलिटी ऑफ मिथाइल साइक्लोहेक्सेन विथ द हेल्प ऑफ चेयर कन्फर्मेशन एंड द न्यूमैन प्रोजेक्शन जोड़ा को ऑलरेडी तमर अछि सी मोस्टली तमर को ये रहइबो साइक्लोहेक्सेन टा मिथाइल साइक्लोहेक्सेन दैट विल रिमेन इन योर इक्वेटोरियल पोजीशन ओके तार एटा ये हे गला कहि एट देखि परिबो कि एक्सियल रे रहिबोनी कारण एक्सियल रे रहिले 1 3 डाइएक्सियल इंटरेक्शन हबो विथ तमरो न्यूमैन प्रोजेक्शन रे शो करिवो कि जेमति तमरो ये जमारो एक्लिप्स टी रे रहुनी okay taku check kariba next this one write the order of simple axis of symmetry and the plane of symmetry in the following molecules okay ei molecule re eta dekho eti bahut gode simple axis of symmetry achi you can have C2 rotation C6 C2 C6 C3 and plane of symmetry eti gode plane of symmetry aschi eti gode plane of symmetry aschi you have different symmetry so this is a very symmetrical molecule tam jodi janithibo it has D6H bond group eti hala C2 axis of symmetry achi ओके ए थ्रू रे जब देखिबो C2 एक्सिस ऑफ सिमेट्री आसुची एठी मोटिके ये हे गला एठी C2 एक्सिस ऑफ सिमेट्री आसुची इवन तमरो प्लेन ऑफ सिमेट्री मध्ये आसुची ए मॉलिक्यूल रे कोनसी एक्सिस ऑफ सिमेट्री होबनी बट स्टिल दिस ऑल दिस मॉलिक्यूल्स आर प्लानर मॉलिक्यूल्स ओके सो एठी प्लेन ऑफ सिमेट्री रहिची Next, how is the asymmetry observed in allenes and spirins different from that observed in biphenyls? So, what example like lekhibo. Okay, explain the method of quasi-racemates for the determination of configuration giving suitable diagram. Dita jack tame khali ye karibo mor quasi-racemate re jota known compound ro suppose dextronally unknown compound ta janine whether it is dextro or levo. So depending on your phase diagram you can just say whether that is dextro or levo rotatory. Okay তারপরে explain the re and c phases of CH3CHO using suitable diagram তার করে কি কোটা re phase কোটা c phase দেখিবো এগুলা সব তো কর পারিবো এতে কিছু অসুবিধা নাই তারপরে এটা 6 number 6 draw the potential energy diagrams for the following reaction indicating step 1 as the rate determining step and step 2 as the rate determining step so you have two steps so rate 1 state 1 as rate determining step means that is slower means it passes through a higher transition state and the second one passes through a lower transition state step 2 as the rate determining step mane first one is very step 1 is very fast but the second one is very slow that means it has a higher transition state so you can just do like this okay how are stereochemical studies helpful in establishing the mechanism of organic reaction jota already कहतली SN1 आउ SN2 SN1 रे तमे R नेइथले मध्ये that is giving you R plus S but in case of SN2 that is giving you R if you have taken R it will give you only S that means it is passing through an intermediate where there is equal chances of attack of your nucleophile from both the sides and in this case the reaction is only that nucleophile is attacking only from the back side so as it is attacking from the back side it is only give you inversion in configuration এই দুইটা example opposite রে okay which is the more stable in the following pairs and why indicate the carbocations as primary secondary or tertiary okay among this which one is more stable if you just see this carbon is secondary okay and this carbon is primary but still this one is more stable as compared to this one because here you have an electron withdrawing group very strong electron withdrawing group is present just next to your carbocation so this is less stable as compared to this one and again in this case CH3CH2 CH plus okay this one is your secondary and in this case this one is primary okay so I think this one will be more stable but this can undergo rearrangement to give you a more tertiary carbocation so this is an ambiguous question actually it has not taken place any rearrangement okay this one is primary not tertiary okay hydride transfer can undergo hydride transfer to give you a secondary. Okay, this one is more stable. Okay, write the mechanism of the following reaction. So here, when this one reacts with water, what happens? So in this case, as you are taking a very weak nucleophile, in that case actually SN1 should happen. So first it will generate this carbocation CH2 plus. So then this that will undergo rearrangement to give you a cycloheptane. Okay, and your water will attack here to generate your cycloheptanol. Okay, arrange the following compounds in the increasing order of their stability. Allyl anion, metanitrobenzyl anion, orthochlorobenzyl anion, benzyl anion. Allyl, this one is your allyl. Sabutokar structure lekhibo. Metanitrobenzyl. Here you have a nitro group. Metanitrobenzyl, orthochlorobenzyl, and benzyl. So you have to see which one is more stable. This one is the most stable anion because benzyl, again you have a electron withdrawing group present at your para position, and this one would be a bit less stable because you have an electron donating group here. So this one would be first, second, third, and this may be fourth. Draw the structures of the two types of carbon, singlet or triplet. Explain the stereochemistry of addition reaction of these two types. So ଯେତେବେଳେ cis addition ହେଉଛି ମାନେ ଯେତେବେଳେ singlet carbon ରହୁଛି you are getting specific products, but in case of your triplet carbon there you are having spin inversion, so that you are getting either cis as well as your anti addition product. Okay, give the evidence which explains the formation of benzene intermediate during nucleophilic substitution reaction of aromatic halides. So you can give the evidence that isotopic leveling study, when anthracene is present, it is undergoing cycloaddition reaction, and when no hydrogen is present at your ortho position, the reaction does not happen. So these are the evidences. You can get more other evidence also, but these three are very important evidences. Why is bromination of free radical mechanism is more selective than chlorination, which we have already discussed. Like in case of chlorination, it is highly exothermic, and in case of bromination, it is less exothermic. So that would be more selective. Okay, write all the possible chlorination products of methyl cyclohexane by photolysis. And just do it. Compare the natures of nitrines to carbons and give two methods of generation. Okay, describe the various redox sources of free radical generation. You can just go on. Okay, I got some this related questions, some from some university questions. So explain why the following bicyclic compound is unreactive towards nucleophilic substitution either by SN1 or SN2. So for SN1, this has to go and you have to generate a carbocation at a bridgehead position. Okay, at a bridgehead position, this can't be planar. So SN1 is not favorable. And for SN2, it has to attack from this back side, so which is also not feasible because of the presence of these bridged groups. Consider the SN1 reaction of tertiary butyl chloride with iodide ion. What will be the rate of formation of the product if the concentration of iodide is doubled? Okay, you remember in this case, I have told that although you cannot generate a carbocation here, but you can generate a radical here, because in the radical case, it does not have to be planar. It can be pyramidal shape also sometimes. Okay. In SN1 reaction, as it does not depend on your nucleophilic concentration, if you double the concentration of nucleophile, the reaction rate would remain the same. It does not depend on the concentration of the reaction. Okay, why bromocyclopropane bromide does not undergo a SN1 reaction, whereas 2-bromopropane undergo bromocyclopropane. Okay, this bromocyclopropane bromide, I just find this one. Okay. Okay, you can just get this type of questions also. Explain Cotton-Hammett principle. What is meant by transition state of an organic reaction? How does it differ from the reaction intermediate? Cotton-Hammett principle means Jahara transition state the reaction will be favored where the transition state is less or the activation energy is less. That way the reaction would be favored. That is your Curtin-Hammett principle. I have given 4 different principles. Then what is meant by transition state and how does it differ from the reaction intermediate? In case of reaction intermediate, it is the local energy minima, maxima actually. And in case of transition state, that it is not a molecular state, but intermediate is actually uh, it has evidence. You can get the evidence of its formation, but transition state you cannot get the evidence. It just passes through that path. Okay, so you can just do this kind of configuration, means reactions. How does this happen? You have to write the mechanism. Okay, this reaction I think we have done, to remove this hydrogen, formation of the benzene intermediate to get this reaction. You can assign the EZ configuration to the following. You can see you have two stereogenic center, your two centers, carbon carbon double bond. So you have to assign E and Z in both, whether what would be here and what would be here, E and Z. Similarly here you have one carbon here, also there. So you can just deduce the EZ configuration. Next, give the stereochemical relationship between the, you can get this type of questions also. Assign R and S configuration, assign EZ, or stereochemical relationship between the following compounds. You can just tell those things. Okay. So any doubt? You can get different questions from the internet if you search actually. And I will say that whatever SAQ and terminal questions are there, you just go through it and actually go through the material thoroughly. Then you just deduce many problems, as many as you can. Okay, any doubt? Okay, if you don't have any doubt, then we can finish today's class. I hope you all enjoyed attending my class. Okay.
Enjoyed, madam, enjoyed.
Yes, ma'am.
किसी डाउट ଅଛି କି?
ମ୍ୟାମ୍ ଯଦି ଡାଉଟ୍ ହେଲା କଣ କେମିତି ଆପଣ କଣ୍ଟାକ୍ଟ କରିବୁ ଟିକେ?
ମୁଁ ଆଇଡି ଦେଇଛି, ଜିମେଲ ଆଇଡି ଦେଇଛି ନା, ଜିମେଲ ରେ ଇଏ କରିବ, କାରଣ ଫୋନ ମୁଁ ଯଦି ରିସିଭ ନ କରି ମାନେ ସେଟା ଟିକେ ରହିବ।
madam, call message ରେ madam mail ଟା
କଲ୍ ହେଇପାରେ ଫୋନ୍?
କଲ୍ ଆକ୍ଚୁଆଲି
madam call message ରେ mail ଟା କରିଦିଅନ୍ତୁ madam.
କ'ଣ?
madam in call messages ନୁହଁ କିଛି।
ହଁ, ତମେ ମୋର ଜିମେଲ କୁ ଫୋନ କର, ଜିମେଲ କୁ ମେସେଜ କର। ଓକେ, ମୁଁ କଣ୍ଟାକ୍ଟ କରିବି ସଦାବେଳେ। ଜିମେଲ ତ ଚେକ୍ କରୁଛି, କିଛି ଅସୁବିଧା ନାହିଁ। ମତେ ଜିମେଲ ରେ କଣ୍ଟାକ୍ଟ କର, କାରଣ ସେଠିରେ ହେଲେ ତମେ ହଁ ମତେ ପ୍ରୋବ୍ଲେମ ଟା ଲେଖିକି ପଠେଇବ, ତାପରେ ମୋର ଟାଇମ ଦେଖିକି ମୁଁ ତମକୁ ଇଏ କରିବି। ଓକେ, ହଁ, ତମେ ମାନେ ଦେଖ, ବହୁତ ଗୁଡେ ମ୍ୟାଟେରିଆଲ ସର୍ଚ୍ଚ କର, ବହୁତ କିଛି ମିଳିଯିବ ତମକୁ। ଆକ୍ଚୁଆଲି ଏବେ ତ ଇଣ୍ଟରନେଟ ରୁ ବହୁତ କିଛି ମିଳିଯାଉଛି, ୟୁଟ୍ୟୁବ ଲେକ୍ଚର ହଉ ବହୁତ ଗୁଡେ, ତେଣୁ ମିଳିଯିବ ତମକୁ। ଆଉ
ଫାର୍ଷ୍ଟ ଟାଇମ୍ ପାଇଁ ଷ୍ଟାର୍ଟ ହଉଛି ତ ମାନେ ଡର ଲାଗୁଛି ମେକାନିଜିମ ଟା ଦେଖିଲେ।
ହଁ madam mechanism ଟା ବଡ।
ମେକାନିଜମ ଟା ପ୍ରାକ୍ଟିସ କଲେ ହବ, ଯେତେ ପ୍ରାକ୍ଟିସ କରିବ ସେତିକି ଅଧିକ ହବ।
ସ୍ଲାଇଡ ଗୁରା ଯେତେ ନେକ୍ସଟ ହେଇଯାଉଛି ଦେହ ହାତ ବିଷାକ୍ତ ହେଇଯାଉଛି।
ମେକାନିଜମ ଅର୍ଗାନିକ ରେ କିଛି ବେଶୀ କିଛି ନାହିଁ, ଖାଲି ରିଆକ୍ସନ ମାନେ ତମେ ଆର ବୁଲେଇବାର ଅଛି। ଓକେ, ମେକାନିଜମ ଗୁଡାକ ପ୍ରାକ୍ଟିସ କଲେ ହେଇଯିବ। ଅର୍ଗାନିକ ରେ ମୋଷ୍ଟଲି ତମର ସବୁତକ ଫଣ୍ଡାମେଣ୍ଟାଲ କନସେପ୍ଟ ହିଁ ବେଶୀ ଅଛି, କି ଇଲେକ୍ଟ୍ରୋନେଗେଟିଭ ରହିଲା, ରେଜୋନାନ୍ସ, ଏଇ ସବୁକୁ ନେଇକି ହିଁ ଗୋଳେଇ ଗୋଳେଇକି ସବୁ ଅଛି, ହେଲେ କୋଉଠି ଇଣ୍ଡକ୍ଟିଭ ଇଫେକ୍ଟ, କୋଉଠି ରେଜୋନାନ୍ସ, ଖାଲି ଜଷ୍ଟ ତମକୁ ସେଗୁଡାକ ମେକାନିଜମ ଟାକୁ ପ୍ରାକ୍ଟିସ କରିବାର ଅଛି। Okay, that's all for today, and that is my last day also today. Okay, bye.
Thank you.
And
you, ma'am.
best wishes for your exam. I hope you all will do well.
Thank you, ma'am.
Thank you, ma'am.
Yeah, most welcome.
Hello.